already put up some stuff on the screen, which is what we kind of went through last class and left off where we were. So let's talk a little bit about what we discussed. Introduced this idea that every valid system, electron, atom, molecule, you name it, satisfies this, what we call an eigenvalue equation. The idea is you have an operator, right, this linear operator that tells you something that's our box. Put in our system, which is represented by a wave function. And out of our measurement box comes a measurement, right, which we call an eigenvalue, which is just a real number. And it has to be a real number, of course, because everything we measure in real life, it has to be a real number, right? There's no imaginary energy or imaginary position. These things don't really make sense. So they have to be real. That really saves our that's a really, really important thing when our wave functions, shoes are falling apart. When our wave functions are complex, you know, if you're doing something to a complex number, you would think you get a complex number out. But we have this wonderful requirement that when we measure our wave function, that we always get a real number, right? Never an imaginary number. Right? And the eigenvalue equation that I introduced is the Schrodinger equation, which is the energy eigenvalue equation. Right? This is every wave function for your system when you want to measure the energy of the system. Satisfies the eigenvalue equation for energy. And our operator, okay, actually I have my laser pointer with me today. Our operator is this H. This is the total energy operator, the Hamiltonian, which is why it's H. Maybe I'll post a nice biography about Hamilton if I don't forget it this weekend, if you guys want a little bit of reading. But again, I'm not interested in history so much in this class, but if you're interested in history, certainly study it. Hamilton, this idea of a Hamiltonian, this idea that the energy, the way we measure energy is kinetic plus potential, this seems very obvious, but this math has been around for a long time. This is Hamilton. There were two physicists, Hamilton and Lagrange, that took Newton's laws and took them up to the next level, if you will. They formalized Newton's laws with modern mathematics, and that's what we use now. When we talk about physics, often physicists don't use Newton's laws. I mean, they implicitly talk about them, but we use these different formalisms because we really care about energy. Energy is the most important kind of measurable, you can say, for any system, right? Every system has energy, so it's a really useful number to measure. And this Hamilton formalism, right, instead of measuring the trajectory of a particle, you're measuring the energy. Really, really powerful and allows you to take Newton's laws and now quantum mechanics and expand it to any system you want. It gives you a very general way to study a system's dynamics. And so we're going to use that formalism, right? So when we talk about how we're going to interact with our particles, the best way to do it is to have a box that measures the energy, the Hamiltonian. Right? That's a really good number. And when we start thinking about, well, how do we probe the energy levels of molecules and right where the energies are, we're going to use light for that. Right? And we know that because particles are waves, it seems very natural to use an electromagnetic wave to interact with our electromagnetic particles that are also wave-like. So we have wave interactions and things. So it's very, very natural to use light for this. And the only thing that you learn from light, right, the only really useful property of light, at least for the most part, 99% of the time, is its energy, right? Its frequency or its wavelength, which is its energy. Right? That's what Planck's law tells us, E equals h nu. That the energy is proportional to the frequency. So it's very nice because if we know something about the system's energy, we have tools in the laboratory that allows us to probe those energies very, very directly. Right? And that's the formation of spectroscopy. Right? That's what we'll get to eventually. So we have this complex operator that's got this second derivative with respect to position and this potential which we have to define for our system. But it gives us a nice equation, right? And we showed this for the particle in the box. Remember the particle in the box, when the particle's inside the box, it has no potential, just kinetic energy. And we get an equation that says that basically the second derivative of the wave function is equal to the wave function times the constant, the energy. And we worked that out really quickly, and we came up, right? We kind of ended class that for this system, that the wave function is a sine wave, right? Our system is represented by a sine wave. That's quantized by the number n, right? And n has to be an integer, right? N's going to be 1, 2, onward and onward. It can't be anything else. You may wonder, why is 0 not included here? Of course, what happens when we have 0? Well, we have 0 energy. All right, you can imagine what that might look like if you have an electron with 0 energy just sitting there. Right? It's just like plop it on the box. It's not moving. But if n is 0, then the wave function is sine of 0 times a bunch of stuff, and the sine of 0 is 0. The only particle that has 0 energy in a box is no electron, no particle. So what that means is that no matter what, right, you could imagine you have this box with an electron in it, and you want to cool it down to absolute 0. Imagine you want to remove all the energy out of the system. Well, the fact of the matter is you can't, because the only 0 energy solution of the box is where n is equal to 0, and there's no electron in it. Right? So the only 0 energy solution is the vacuum. Right? So by definition, the electron in the box has to have energy. Has to have energy, because n is equal to 1. And its energy is h squared over 8 ml squared, where n is the mass of the electron and L is the length of the box. That's really, really, really critical. And we'll see this time and time again. Right? It says that no matter what, our electron will always have some energy, residual energy. And the absence of energy means the absence of the particle. Right? So it's literally impossible. Let's say you have a gas of electrons or atoms in this box that don't interact. So it just acts like n particles in a box. You can't cool that system down to 0 Kelvin, because those particles always have energy, and the minimum energy they can have is h squared over 8 ml squared, where n is 1. So no matter what, you can't get to 0 Kelvin. There's always residual energy. Right? That's a really, really important consequence, because in classical physics, what is the 0 energy state of a ball? Well, the 0 energy state of a ball is a ball that's sitting by itself, not moving. Right? It's very easy to have a 0 energy system. When people take naps in here, they have a minimum energy to go to 0, right? But electrons don't take naps. It's impossible for them to remove their energy. They always have it. That has very, very deep consequences, because what it says is there's no 0 energy state. All right? And what actually the consequence of this is it's deep. But one thing you can think of is that the electron in some ways is literally in of itself a ball of energy. Right? The only way to have 0 energy is to have no electron. So the electron itself is an energetic particle, just by definition. And of course, the way to see that is, again, at low temperature, at low speeds, you don't really see this. But if you make this electron move really, really fast, if it's moving at relativistic speeds and things like that, of course, the energy of the electron is its mass times c squared, right? E equals mc squared. Right, so just the presence of the electron imparts some amount of energy. The electron in of itself, in that it's a massive particle, is an energetic one. Okay, that's purely quantum mechanical, 100% quantum mechanical. Right? Because if it were a classical ball, it can have 0 energy, it's at rest. But the point is that if you put an electron in a box, it never is at rest. It's impossible. The only way for it to be at rest is if it doesn't exist. All right, so there's a term for this concept. We'll see it again when we talk about bonds, because it really rears its head in bonds. We'll talk about the quantum mechanics of a chemical bond. But this idea that the electron always has energy, so the electron never has E equals 0. This residual energy, if you will, right, the ground state energy of the electron, right, n equals 1. We have a term for this. Instead, it has a residual energy. It has an inherent residual energy. No matter what, no matter how cold it is, which is n equals 1. And the term for this, we'll define it more carefully soon, is called 0-point energy. Zero-point energy. And it is uniquely quantum mechanical. It's one of the first results. We're going to see systems, though, it's very interesting. We're going to see systems, though, that show different behavior, too. For instance, as we'll see in bonds, again, bonds will also have quantized energy levels, which represent, so for instance, in a stretch, where your bond is stretching, there are quantized levels of stretching. There's n equals 1, n equals 2, but there's also n equals 0 for the stretch, which is a bond that doesn't stretch at all. All right, for that system, n equals 0 is defined. A bond at n equals 0 is not an invisible, non-existent bond. It's a bond with no energy in it, or no excitation in it. But it still has residual 0-point energy. So even though the particle, so effectively you've never placed any energy inside of that bond, it still vibrates with a little bit of energy. Right? And that's what's called 0-point energy. And every particle has this in quantum mechanics. If it's in a bound system, right? If it's in a box of some sort, or in a potential, it will always have this 0-point energy. And this is intrinsic and essential to quantum mechanics, this concept. Right? We'll explore it more as we go through. So we don't quite have the postulate to explain it yet, but we will. It turns out one of the reasons why things have 0-point energy is associated with the exact same reason why you can't measure color and flavor in an electron. That consequence is directly related to the point of 0-point energy. Right? These are all interrelated concepts, and they'll all come out together. Right? But we're just seeing little cookie crumbs as we go. But they'll all come together in a great kind of revelation that all of these kinds of weird behaviors are all associated with the same kind of fundamental principle, which is that you have these wave-like particles that vibrate. Right? They have wave property and particle-like properties, and this dichotomy between wave and particle is essential to the fact that they have 0-point energy. It's directly connected to it. This idea that you can only measure one thing at a time, that you have incompatible measurements, and that leads to this result. A particle at rest, the idea is that a particle at rest, as we'll see, it's not moving. It has some uncertainty in its momentum. So if you know exactly where the particle is, right, if we localize the particle as much as we can to a position, it turns out the momentum, the error in momentum is maximally large. And remember that energy is proportional to the momentum squared, p squared. So if you have some variance in your momentum, what that means is the particle might be moving left and right. It has some velocity, but you don't know it. There's some uncertainty. That means there's some uncertainty in p squared, which means there's some uncertainty in energy. And so you end up getting some residual energy because of this, because of the fluctuations. Because everything's random. You have these little fluctuations in energy, position, and momentum. And these lead to that residual energy. And you just can't get rid of it. This is a big problem. Because if every electron at the coldest possible temperature, people had problems with this for a long time. If everything was at the coldest possible temperature, you might have 10 to the 50 electrons in the universe. They all have this little residual energy. Right? So what does that mean? Well, that means that the total energy of the universe is massive because they all have this residual energy. And people thought, well, that must mean that why is it that the temperature of the universe isn't infinite? Everything has energy. There's no zero energy particles. They all have this residual energy. Everything should be glowing white hot, but it doesn't. Right? So there's a lot of really complicated intricacies here. But the fact of the matter is that you can always measure the 0-point energy. It's intrinsic to quantum mechanics and chemistry. In fact, it plays a huge role in chemistry. You might not know it, but we'll see as we go through this class instances where this concept that bonds always have some residual energy, it has direct chemical consequences, both in reactions and in structure. Okay, so let's be some more practical. I want to talk about particle in the box today. And where we left off was, again, we had these sign functions with this energy. All right, we'll look at this today. I have some pretty pictures for you. Well, what we need to do is we haven't figured out this B constant yet. That's what we left off on. But there's this constant B we haven't defined yet. So we know what's inside the sign, but we don't know what's on the outside. So we remember we got rid of the cosine term, the A cosine kx term. That goes away because of the boundary conditions. And we also got this inside because of the boundary conditions. But we haven't figured out what this B term is, so let's do that today. Really, really easy calculation. And let me get my notes just in case. So the way we're going to figure out this B term, the constant term on the outside of the wave function, we need to define it so it satisfies all the properties of a wave function. And the one property we haven't figured out yet, or we haven't applied yet from our postulates, is that the function is normalized, that when you integrate it, you get integration of 1. When you take the square of the wave function and integrate it over the box, you get a 1 out. Right? So our wave function for our system, psi n of x, just remind you, it's b sine n pi x over L. All right, and so the way we're going to solve for b, and this is the way we solve for these coefficients, this is a general approach to this, is use the fact that the square of the wave function, the integral of it, is 1. So we know that when we take the integral squared, and integrate over space, over the box, which is going to be between 0 and L, we get a 1. All right, this is our normalization condition. So we know the function, we've already defined the interior, so we should be able to use this as an equation and solve for b. These are only unknown. Right? We know what the integral equation is, and we can solve for b. So let's do that. So let's see. So what do we get? Well, we plug in psi. We get, again, the integrals from 0 to L. B squared sine squared n pi x over L dx, which has to be equal to 1. Okay. So let's do a little bit of simplification to do this integral. I'll show you guys in a second. All right, before I forget, I'll pull it up near the end of class. In this class, we're going to have a lot of integrals that are of the same style. In fact, in particle in the box, everything can be sines and cosines. You're going to take integrals of sine times cosine, sine squared, all this junk. You can do them on Wolfram Alpha. I also have a table on Canvas in Module 0 of common integrals in this class. So most of the integrals in this class you can just look up and solve. You don't have to do them yourself in case you don't remember how to integrate sine squared. The fact of the matter is I forget how to do it. But you'll find that the integrals in this class, as we'll see as we do problems and examples as we go through these toy models, you see the same things over and over and over again. It's in some ways, the math in this class is very repetitive because we have a wave function and it tells us everything. So there's really nothing to do besides integrate the wave function. Here, that's a sine function, so you're going to see a lot of integrals of sine. All right, and occasionally we're going to have to take derivatives of sine, so then you'll get a cosine as well. And we'll see that today. So we just need to solve this equation for b. So what I'm going to do is I'm going to integrate out, I'm going to factor out the b squared. It's going to be integral from 0 to L of sine squared n pi x over L dx is equal to 1. All right, and now to solve this equation, I need to use u substitution. So my u substitution, I'm going to let u be n pi x over L du is n pi over L dx. All right, and of course when we do u substitution, we also have to figure out what the bounds of our integral are because they're going to change by a linear factor. And the bounds of the integral, so we start from 0 to L. And once you do a little bit of math, it's not hard to see that the integral bounds of this changes to 0 to n pi. All right, so we're going to integrate the function from 0 to n pi. So what do we get here? We get b squared integral from 0 to n pi of sine squared u du. Okay. And again, I can just integrate this on my calculator. You know, this is a very easy function to look up. And once you do this, you get the following result. B squared L over n pi times n pi over 2. All right, so where do these numbers come from? Well, the b squared, again, comes out of the factorization. The L over n pi comes from the du factor here. And the n pi over 2 comes from the integration of sine squared. So the integral of sine squared u from 0 to n pi is n pi over 2. Okay, so this is the integral result. This is my u substitution, and this is my coefficient. And of course, this all has to be equal to 1. All right, so we have a really, really simple algebraic equation to solve. All right, and it's really easy to see how this solves, right? The n pi's cancel out. Right, we have b squared L over 2 equals 1. So b is equal to the square root of 2 over L. Like that. All right, this is what we call our normalization constant. Right, the fact of the matter is that sine of n pi x over L is a totally valid solution for the Schrodinger equation. It's a real wave function. But it doesn't integrate, the square root doesn't integrate to 1, right? It integrates to, if the b is set to 1, it integrates to L over 2. If b is 1. So if we ignore the normalization constant, it integrates to L over 2. This is not 1. So in order for this to all equal 1, we need to set the b to square root of 2 over L to cancel out the L over 2 factor. Okay, very simple. So this is our normalization constant. This takes the wave function and sets it so that it integrates to 1. Okay, right, that's our big property, right? That it integrates to 1. Right, you can kind of think of this as the length of the vector, if you will. Square root of 2 over L. All right, and we're done. We literally now have defined exactly every possible energy state of a single electron inside of a box. We have everything we need to know about it. We know the wave function precisely. We know the Hamiltonian. We can calculate the energies. And we can ask questions to our wave function now because we know everything about it. Right, we fully solved this system. All right, of course it doesn't mean a lot because, again, it's just a function. All right, so let me just put this all together for you just to have a nice picture. All right, so the particle in the I'm going to call it PITB, pain in the butt, particle in the box. Right? That psi n of x are wave functions, square root of 2 over L, sine n pi x over L. And our energies are n squared h squared over 8 ml squared. Right? This is our particle in the box solutions. This is the exact solution for the behavior of the system. Exactly. Right? You can make boxes and put particles in them. There's a concept called optical lattices in physics where they use lasers. They use a sequence of lasers to build an electromagnetic box that you can trap a particle in. Right? So instead of having physical walls, they have walls of high-powered radiation that pushes when the electron comes close to the wall, if you will, of radiation, and bounces off. Right, so you can make boxes, three-dimensional boxes with lasers, 2D boxes as well, 1D boxes with lasers. And the physics of those particles inside of those little boxes is exactly this. And you can even use models, for instance, when you think about atoms on top of a surface. Think if you have a surface of metal, and you want to, like for instance, when you're doing catalytic conversion, when you're breaking down hydrocarbons and things like that inside of after combustion, the way that the people often model the kinetics and the dynamics of that catalytic conversion, the process of unreacted hydrocarbons breaking apart into CO2 and H2O and all of these things on a surface, a palladium surface inside your catalytic converter, the way you can treat the catalytic converter surface is having like little holes where the molecule sits, little boxes where the molecules can get trapped in. There's some requirement of energy for them to get out of the box and move to a different one. They call that hopping. And you can use these math to model that. So you have a bunch of little boxes with very small probability the electron or some particle or atom leaving one box and going into the other one. And the way that energy and those physics work is exactly this. Each one of those boxes, each one of those little holes inside of the metal surface where the molecule goes, can be measured as a little box with a particle in it. And so you can manipulate your particles in those systems with a laser and get them in the right energy level to increase their reactivity. Right? If you put them in an energy level, you know exactly where that energy is, if they have enough energy to kind of pop over the box, then you can do that and you can accelerate your reaction conditions and your modeling. All right, so this is very, very useful. There's lots of different cases, and I'll show you, hopefully on Tuesday, a chemical application of this that's direct. Right? And in fact, in the third rotation of PChem lab, the dyes lab, as we call it, is a literal chemistry experiment that uses the particle in the box model to explain how dyes work. It's a very, very powerful technique. It might seem very trivial, but there are a lot of boxes in the world, and there's a lot of particles we put in boxes. All right, so let's see what this looks like, okay? So what I have, here's a little show and tell for you. So what I've done now, the nice thing about having this is I have an equation for everything. So what I can do is I can just start making wave functions and calculating their energies and putting them on a plot. So here I've got a really simple Python script that generates any particle in the box wave function I want. I give it the n, I give it the length. Those are the only two variables you need, and the mass. And it calculates the energies in the particles and the functions, the wave functions. So let's just take a look at what the wave functions look like. All right, so what do they look like? So let's go ahead and get this started. So let's look at like the first 5. All right, so I'm going to let n equals 1 to 5. And let me make the figure a little bigger. Sorry. Okay, so here's the first 5 wave functions of the particle in the box, and they're kind of hard to see here, but there's little gray lines here. These are the energies of each of the levels. Right, so here's the n equals 1 level right here. Right, I'll just write it on the board just so we know what the function of this looks like. I had a blue marker, and no, I don't. Okay. All right, so this is sine, so the n equals 1. I'll write them over in the middle so everyone can see. N equals 1 is sine pi x over L. All right, now let's think about, as you can see, it's only a half period of the wave. Right, and that should make sense. Let's see, sine of 0 is 0. That's good. Sine of L would be pi L over L. That's pi. That's 0. And so, and you can find that the maximum of the function will be at L over 2. So you just get one peak. And so you just have this nice little curve here. Right? So this is your first sine, your first big function. This looks kind of like a broad single half note. On the right is psi squared. All right, remember that psi squared is really what we measure. The wave function is probably complex. In this case, it's not. But we don't actually directly observe the wave function. Remember, the Born interpretation says that the only thing that we can measure is the probability of the particle, which is psi squared. Right? So the actual measurement that we make of the particle, what we see on our screen when we measure the particle as it moves through the box, or we make measurements of its position. Maybe that's a better way to think of it. Imagine we put an electron inside the box at n equals 1, so it's at this energy. And every once in a while, we make a measurement of where it is. All right? And then what we do is we make a function, we make a plot, which is the x-axis is position on the box, and the y-axis is the number of counts seen at that point. Right? That's like, think of like a histogram. Right? It's the number of times we observe it at that position. That's what psi squared is. Right? So what does psi squared say? It says, well, on the edges of the box, there's very low probability of seeing the particle there. The particle tends to exist in the middle of the box because the probability is higher there. Right? So we would say, so we could calculate an average, for instance. We'll do this and prove it. What's the average position of the particle at n equals 1? Oh, it's going to be right in the middle. Right? So on average, the particle's in the middle. And then you ask, what's the standard deviation? What's the variance of the position? Well, it's quite broad, right? It can be, right? If you think about the standard deviation, it's about this big. Right? So even though we know the average of the position is right here in the middle, we have some uncertainty, inherent uncertainty to that. Right? And the psi squared tells us that. Right? There's a standard deviation to our measurement, inherently. Right? We can't do anything about it. Right? If we fix our particle at a specific energy, this is what we get for the position. right? And that means that the particle is actually delocalized, right? It has an average, but it also has a standard deviation. Okay? It turns out that if we wanted to make the particle exact, what if we wanted, let me just kind of draw this. Imagine we wanted to localize our particle so that psi squared looks like this, right? The particle is exactly there. Right there. Okay? And you ask the question, what's the energy of this particle? Well, that would also be asking, what's the momentum? And when we measure the momentum of this particle, right, remember that energy is proportional to p squared. Right? And so when we measure, this is in position, so when we measure the momentum of the particle, what you end up getting, the momentum of the particle looks like this. And so if we were to take the square of it, momentum squared, and divided by 2m, that's the kinetic energy. The momentum of the particle in momentum space is completely delocalized. It's at all energies. Okay, so we always have a trade-off. We can either have a particle at an exact energy, and therefore its position is delocalized, or we can have a particle that has a very, very precisely known position, but then its energy is distributed over many, many values. Right? The idea is that this function right here, you could write it as an infinite sum of sine waves. And each of these have an energy. Each have a momentum proportional to h bar and h bar k. So a particle that's perfectly defined has a perfectly undefined energy spectrum. It's a sum of all the possible energies the system can be at. So we have to always make a choice, and we'll formalize this limitation. Eventually, that's what's called not the Pauli exclusion, it's called the Heisenberg uncertainty principle. That there's always a trade-off between our knowledge of energy and our knowledge of position. All right, so if we want to know the particle exactly, we can't know its energy exactly and vice versa. All right, we get this delocalization. All right, so, but again, this is, in some ways, this is the best we can do because energy is what drives chemistry, what drives physics. So it's really the information we really care about is the energy. So when we define the energy exactly, and we define our system to have exact energy states, n equals 1, n equals 2, n equals 3, then we lose information about the position. Right? The system delocalizes like a wave. But the nice thing is that we can still calculate averages. Right? That's the important thing here. Is that this tells us exactly where the particle is probably going to be. Right? It tells us the probability. So we can take averages, we can do statistics on it. Right? I can define exactly what the average measurement I'll get and what the standard deviation of my measurement will be. But I can't tell you the exact position. Right? And that's what the wave function tells us. It's the best we can do. And again, it always depends on your perspective, because maybe it would be interesting to think about the particle being localized in a position because you're doing it like a projectile, right? But if you have a projectile electron, it might be useful to know its position, but you lose information about its momentum and its energy because of that. Right? So there's always context about these things. And it doesn't mean that a particle with an electron with exact position and an electron with exact energy are any different. They're the exact same particle, but we can only measure them in one context. Right? It's a limitation of us, this. This is just the way a particle works. It still can be a particle of exact energy, it can be a particle of exact position. It's still the same electron. Nothing's different about it. It's totally fine. But unfortunately, our limitations, when we take this behavior and put it in a classical measurement context, where we measure it ourselves on our classical chemistry lab, we have a limitation of what we can measure simultaneously. Right? We have to make a choice. And in this class, we almost always make the choice in terms of energy because that's what we care about, right? Because we're chemists, we care about stick spectra, right? We care about transitions in spectroscopy and molecular orbitals and atomic orbitals. These are all states and representing states of defined energy, right? These are the states that we're probing with our laser or with our light source. Or these are the ones that represent our chemical interactions. Right? Because chemistry is just energy. It's just transfer of energy. So anyway, I'm going to keep going a little bit here. So again, n equals 2, n equals 3, n equals 4, n equals 5. And you can see that as I go up, right, the frequency of the wave is increasing. Right here I have one whole period of the wave. No, sorry, 2 whole periods of the wave. And here I have 3, 4 periods, 5 periods. Now here's the interesting thing about this. Oh, I'm drawing the board. Look at n equals 2, for instance. Now the particle, right, remember this is the probability where we find it. Now if the particle's at n equals 1, we don't see it in the middle anymore. There's 0 probability the particle's ever in the middle of the box. It can never be here. But instead it's here on these edges. Right? And you can see that as n increases, right, you have the troughs and the valleys are happening more and more rapidly, so the kind of like space that the system can be in kind of expands, right? The particle kind of starts to fill the box more evenly. Because you look at n equals 5, there's 5 peaks there, right? There's 5 kind of high probability regions the electron would be in versus 2. Right? So as n increases, what that means is the electron kind of spreads out. Right? It can be in all sorts of positions. Right? So let's take this to the logical maximum. Before I say anything, actually, I'll write this down and we'll see this again. These places where the probability is 0 inside of a box, they're called nodes. I'll write them down later. We'll look at them later. Nodes. And nodes are a very useful thing to count. You'll notice that this one has 1 node. We don't really count the edges as nodes because it's 0 for all of them at the edges, right? So this has 1 node. There's 1 place where the electron can't be. There's 2 places it can't be here, in n equals 3. 4 places it can't be here. Sorry, 3 places. Sorry, 2 places, 1 place, 2 places, 3 places, 4 places it can't be in the middle of the box. And what you can see is that the number of nodes increases, the energy increases. In fact, they track, right? The number of nodes is n minus 1. And the energy is increasing as n squared. That's general. In general, you can actually, if you have a set of wave functions and you want to identify which one's higher energy than the other, and they all come from the same system, you just count the nodes. The less nodes it has, the lower energy it is. All right, we'll look at why that is when we talk about molecules, where nodes become very important. But that's a very general concept, is that the nodes have the fact that there's these 0 probability things actually are represented or correlated with high energy. And again, that's just because of the wave nature of part matter. Right? Higher energy means higher frequency waves, which means more nodes, right? You go through more periods of your wave in a given region as you get a higher frequency, higher energy. And so therefore, node count is proportional to energy. Right? The more nodes, the higher the frequency, the higher the energy. All right, so let's just take this to an absurd maximum, and let's look at like n equals 90. Let's look at like n equals 95 to 100, right? Oh, it didn't like that. Oh, I know why. I wonder if it's this. Well, this was working yesterday, so let's see. Okay, well, anyway, I'll draw it on the board. I will draw it on my thing. So what happens when n is getting really large, right? That might be an interesting thing to think about. Well, again, if n is large, if n is 100, right, so example, n equals 100, right, there's going to be 99 nodes and approximately 99 peaks. Right? So if I were to plot this wave function squared in my box, right, it looks like this. Well, actually, it looks even closer than that, right? It just looks like a bunch of peaks oscillating rapidly, right, like that. Right? And you can imagine I just take that limit to the extreme. Right? Imagine I take it to n equals 1,000. Right? At this scale, at n equals 1,000, so I'll write this as n equals 100. And then at n equals 1,000, at this scale, it basically looks like a solid, right? It basically looks like a flat line, like this, with a bunch of like crap in the middle, right? But you can't see the peaks and the troughs anymore. Right? So how do we interpret this? Well, remember n equals 1. N equals 1 is just this broad hump. Right? It just goes like this. Right? So there's a very clear place where there's an average position right in the middle of the box at low quantum number, low n. But when we get to n equals 1,000, effectively the thing is oscillating so fast that if you look at the scale, it just kind of looks like a flat line. Right? The peaks of your sine wave are so close together. There's so many of them, and the frequency is so high you don't really see it oscillating anymore. So it kind of looks like it has a flat probability. Right? And what would we expect for a particle that's classical? What would psi squared look for a particle that's moving at 300 Kelvin, just like a gas particle? Well, remember in ideal gases, right? What was the assumption? The assumption is the particles move randomly in the box. They fill the space. Therefore, there's an equal probability of the particle being anywhere in the box. Right? That's exactly what we see at n equals 1,000. Right? As n gets greater and greater and greater, you put more and more energy into the electron. It gets to the point where the probability distribution, psi squared, just looks like a flat line at this scale. Right? And so what's happening now is that classical behavior is appearing. Right? Classical behavior says that if it were a classical particle in this box, there's an equal probability at any position to find it. Not in the center, not on the edges. It's the same everywhere. Right? And we see that behavior when n gets very, very large. Right? This is what's called, let me just write it down, the homework 2. This is actually the point of homework 2. So at the limit of large n, the behavior of classical gases or classical particles naturally arises. Classical particles. Classical atoms, gases, whatever. Right? They have a uniform probability distribution. Right? It's the same value at every point. Right? That the psi squared at high n, as n goes to infinity, starts to approach a constant value, whatever that value may be. Right? And this happens in all quantum mechanical systems. This is the thing that really started making people believe that quantum mechanics is a real thing. Is that when you take a quantum mechanical particle and take it to energies that are classical, right? Like an atom at room temperature, you get the classical behavior back. Quantum mechanics smoothly moves into the classical regime. So you get all of Newton's equations back. You get all of thermodynamics back. All of that is still true. And it happens at the limit of high n, where energy is very large. This is what's called the correspondence principle. Right? That a valid microscopic theory for the system should lead to the exact results you get from classical mechanics or thermodynamics or ideal gas or whatever. at the limit of large n, or high energy, however you want to think about it. And this is true for all systems. All right, so that's a really powerful thing, right? Quantum mechanics really isn't its own little beast. It's just a different shade of classical physics. Classical physics, or we put it this way, classical mechanics is a different shade of quantum mechanics that appears at high energy. And so the homework a lot explores this. All right, so this is actually the point of the homework. So you're going to use the particle in the box, and you're going to look at how the position, the probability distribution of the particle changes first as you go from a small box at really low temperatures to a macroscopic meter cube box, like a macroscopic box at room temperature. Right? And you'll see that the kind of behavior that you expect from a gas, in this case we use helium atoms instead of electrons in the probability in this problem set. If you have a gas that's of helium atoms that's very, very cold in a very small box, it acts very quantum mechanically. Right? So it's less like n equals 1, right? It has this it is a non-uniform probability distribution. But then when you put the same set of particles at 300 Kelvin in a room-sized box, you get classical behavior back from it. So it's not like quantum mechanics is an entire different universe. It's just something that emerges at low energy, at low n. Right? And these numbers, n's, are so important. Every system, every bound quantum mechanical system, what I mean by bound is I mean it exists in a potential that it can't escape. It's not just free to move, but bound particles will always have states that are quantized. They'll always have these numbers, n. They'll always be indexed, right? There's always discrete numbers. And there's a term for these numbers. I just want to introduce it, because I'll use it a lot, and I don't want you to get confused. These are called quantum numbers. There are little indexes that tell you, again, what energy level you are at and stuff like that, right? They're useful. But every system has a quantum number associated with it. Some systems have many quantum numbers associated with them. Right? For instance, the hydrogen atom has 4. Right? Every state in the hydrogen atom can be represented by 4 indices. Right? We'll see those indices. You already know some of them. You know for instance, you know 1s, 2s, 3s, 4s. There's that 1, 2, 3, 4. That's n for the hydrogen atom. There's s, p, d, f. That's what's called the L quantum number. For the p's, there's 3 p's, right? There's the px, the py, and the pz. There's 3 of them. That number is called m sub L. And then there's also the spin up and the spin down, which is the spin part of it. You have 2 electrons per orbital. That's called m sub s, the spin number. Right? So there's 4 numbers that define every state in the hydrogen atom, just like there's 1 number that defines every state in the particle in the box. Right? Quantum numbers are super important because if you can, right, when we talked about the atomic spectra with Balmer and Lyman and all those old guys were looking at these spectra and doing numerology, right? They were picking the lines out and fitting into a function that was a function of a number, right? This is the first line, the second line, the third line, right? Very, very basic spectroscopy. Right? They were implicitly using quantum numbers here, right? They were indexing each line in the sequence from hydrogen to a number. And implicitly, these are these quantum numbers that appear. Okay? So we'll see this over and over again. Every system, we're always looking for the quantization. We're always looking for the quantum number. We're looking for these discrete levels of energy. And we're going to find them absolutely everywhere. Okay. Now, that's about as much as I could talk about this, right? So we have a wave function. We have its square. I'll go back to it one more time. Let's look at the pretty pictures, if it lets me. Let me go back to 1 to 5. Right, psi squared is on the right. So this is what we see in our measurement. Right, for each of our energy levels for our particle, we see these little plots of our position, probability distributions. But what else can we do with them? Right, this tells us kind of roughly where the position is. But maybe I want to take some, right, I got to do statistics on it. I need to start asking questions. And the fact of the matter is that the best thing we can do is take statistics on this, right? We can take an average, we can take a standard deviation, we can take a variance, we can do things like that. because things are delocalized, right? For instance, we're going to ask what position you're at. Well, the best thing we can do is ask for the average and the standard deviation, right? So we should come up with a way to do that, right? How do we take averages? All right, and this is actually super important. This is one of the key principles of quantum mechanics. Because the fact of the matter is these systems are waves, right? Everything has a probability distribution, which means that it only has a probability of being somewhere, but it's random. So we have to take statistics on a random, this is a random distribution. So we have to take, the only thing we can do is take statistics. So we should learn how to take the statistics on wave functions. And it's a very, very easy formula. And there's only one formula. And it works for everything. All right, so this starts the next postulate. Postulate 4. Average observables. My computer's freaking out. Hold on a second. I don't think it's crashing, but it might be. It crashed. You know, I don't have this problem in the other room, in Buckman, and I think the reason why is because it's so damn hot in here, and my computer's like thermally throttling itself in here. So I need to bring in like an ice tray or something like that to keep my computer cold. Thankfully, I have been saving this, so I should be able to just recover it. I've probably missed the first slide. Okay, well, I've missed a few slides, but that's all right. It'll be on the video. And I'll have tomorrow's slides for you guys as well, because it'll be the same lecture for Thursday. Okay, postulate 4. Average observables. Okay. All right, so let me write down the kind of general statement first. So if a system, particle or whatever, is in a state described by a normalized wave function, psi, draw psi like that, the average value of an observable, so position, energy, you name it, corresponding to operator O, can be calculated as follows. All right. So when I write an average, we have a symbol for that. So the average value of the O operator I put in these little angle brackets. This means average. If you've taken statistics, you might have seen this notation before. This is an average. And the average is done just like the normalization. We take the integral over the space of our system. So our box would be 0 to L. Of the counter of the complex conjugate of the wave function. If it were a real wave function like our particle in the box sign, it's just the wave function itself. Times, I'll write it in parentheses, the operator acting on the wave function itself. D, whatever the space variable is, dr. This. Okay, so what we're going to do, in order to calculate the average of something, we're going to take its operator and jam it between psi squared, right? If O was just 1, right, just the identity, you could factor it out, and you'd have psi squared, right? So we're going to jam the operator in the middle of them and multiply it all out, right? And the way this is done is we're going to operate on the wave function first, and then multiply it by its complex conjugate, or its wave function, in the case of a real function. All right, so let's look at how this works. So for instance, let's take the average. All right, let's take the average position. for n equals 1. All right, for the weight particle in the box. Okay, so what would this look like? Well, this is the integral from 0 to L of the complex conjugate of sine, but that's just sine, there's no i's. So we just put the function here. I'll write that here in just a second. I'll write this here. If psi is real, psi star is equal to psi. I'll put that in the little box there, just for you to know. There's no i's to flip to negative, so it's the same function. All right, and what's the operator for x? Well, if we go back to that table that I wrote down a couple days ago or last week, the operator for x is just x. So we're going to take x and apply it to sine n pi x over L times dx. Okay? All right, and we can just integrate this straight up, right? I'll do some simplifications. We also have a factor of 2 over L, I'm sorry. Each one has a factor of square root of 2 over L, so there's a factor of 2 over L out here. Right? There's that normalization constant. So it's squared, we can just factor it out, 2 over L. Sorry about that. Let me erase this. Right, so the nice thing about this operator is that it's an algebraic variable. We can rearrange this function freely. It doesn't really matter what order we take things in. So we can write this 2 over L integral from 0 to L of x sine squared n pi x over L dx. Right? And that's the average. We can evaluate this. We'll do it in just a second. This is the average of our function, of our variable. Right? So we should get a number out of this because it's an integral, a definite integral. That's going to give us a number. Right? So we'll get a number that's proportional to L. Right? Because remember, our position is a function of L. Right? It's between 0 and L. So we're going to get some fraction of L, whatever the average might be. Okay, so this function, in order to do x sine squared of x, to do this, you have to do u substitution, and then you need to do integration by parts, which I don't want to do. So let's just go ahead and let me pull up Canvas really quickly for you guys, and let's just look up the resource. And again, you could type this into Wolfram Alpha, and it'll do it for you too. And here, n is 1. I forgot to write that, but n is 1 here. We'll fix that in a second. But let's go ahead and look at some, let's just see if we can look it up in the table. So on Canvas, I have this table of useful integrals for quantum mechanics. God, I hope this still works. It does. Every function you'll ever need in this class is in here. So we need to integrate x sine squared x. So we've got rational functions, basics, integrals with roots. Let's keep going. Let's see if we can find trig functions in here. Here we go. So now we have trig functions coming in, right? So there's my integral for, of course, you know the sine x, sine squared x is x over 2 minus 1/4 sine 2x, right? You have all these nice formulas you can use. So let's look for x cosine squared x, which is really close here. Let's see if we can find it. There's x cosine x. Where's sine squared? Well, I thought it was in here, but it's not. Does anyone see it? I don't see it. Well, maybe this isn't as useful as I thought it was. Well, that's unfortunate. But anyway, so let's go ahead and do it on Wolfram Alpha. All right, let's just do it really quickly. So let's do, let's just see how this works. So we're going to integrate 2 over L. Oh, sorry, let me do it like this. Let me do it properly. Math input. Let's integrate 0 to L of 2 over L. Sorry. We have a 2 over L on the outside. We have L to 0 of x times sine of x of n was 1 here, so we have a pi times x over L dx. And this is squared. think that looks right. So we remember our function is x sine squared x. N is 1 in this case, so we have a pi times x over L, all squared from 0 to L. Go ahead and calculate that. And here it is. The result's L over 2. All right, very nice. All right. And again, we'll see this integral a lot. Right? So this whole thing ends up being L over 2. Right? So our average position of the electron is L over 2. It's halfway through the box. So let's go back and look at our wave functions. So this box is running between minus L over 2 to L over 2. The middle's in 0. Right? So the peak of the probability function, the mean, right? The peak of your probability distribution, the mean of it, is right in the middle of the box, L over 2. Right? So just doing statistics on this. And so let's start thinking, let's go to the next one. Right? So how does this change as a function of n? Right? So let's go to the next energy level. How does the average position change? Well, let's cut these functions in half. Right? And if you notice, the function on the left side of the box is the same as the right side of the box. Right? So there's equal probability to be on the left side of the box as there is on the right side of the box for any level. It's not hard to show. And in fact, I think part of the problem set will be to do this is that, again, the average is going to be the exact same. There's equal probability to be on the left side of the box as the right side of the box. So the average is in the middle. All right? So the average for every wave function is L over 2. There's always a probability. The average place the electron is going to be is L over 2, right in the middle. But as you can see, that doesn't really tell you a lot. Because the distribution of where the particle is as a function of n is very different. The average is the same. But as you can see, the probability distributions are very different. In fact, as n is getting greater and greater, there's a larger probability to be on the edges than there are to be in the middle. A really good example is n equals 2, right? You can't be in the middle on this one. You can only be on the edges. Right? And that continues to go. So what is actually happening here? Well, the standard deviation, the variance, right, the width of your distribution is widening. So even though the mean is constant, because these functions are symmetric about the center, the standard deviation of your measurement of x is increasing as you go up in n. Right, so how would we calculate that? Well, I won't do it here on the board because it's a part of your homework. But how would we calculate the standard deviation of our distribution, right? When we talk about grades, the average is important, but also the width of your distribution, the standard deviation is important. So we need to step up our intricacy a little bit, right? So for the particle in the box, for the PITB, x is equal to L over 2 for all n. Okay? But what I want to measure is the standard deviation. What is the standard deviation of x? Okay. Well, you can use a little bit of statistics and go back into your statistics text, and they give you, if you know what they call, if you know the average, they call the first moment of your variable, and you know what's called the second moment of your variable, you can calculate the variance of it. And there's a very, very simple formula for this. It says that, so this is the variance, this is what's called the variance, I don't know what you call it, I'm going to call it the variance formula, which says that the standard deviation of a variable squared, let me give this a better color because I think the purple, put it in yellow. So the standard deviation squared, this is the, so I'll write it in a second. So this is variance. It's called variance, which is sigma squared. And standard deviation is just sigma, so it's a square root. Right? Is equal to the average of the variable squared minus the average of the variable squared. That sounds the same thing. But you can see the difference. Here I'm taking the average of x squared. This is called the second moment in statistics. So the second moment of the motion, x squared, the absolute magnitude squared of your motion, minus the square of your average. Right? So we already know what that is, right? This is L over 2. So this part of the formula is L squared over 4. Right? So we have to calculate this, though. And this is perfectly general. Right? This is true for all variables. True for all measurables. Okay? I have you go and do this calculation in the problem set, right? But let's just kind of set it up really quickly, just to kind of think about it. I won't have to do the calculation. It's not too hard. But we know how to do this, right? So for the particle in the box, so my example for PITB is that x squared is going to be the integral from 0 to L of sine n pi x over L times x squared sine n pi x over L dx. Right? And we know x is L over 2. Right? So the standard deviation for x is going to be the square root of whatever x squared is. I'll have you evaluate that in the homework. Minus the square of x, which is L squared over 4. What you're going to find, so again, what does this mean? Right? Standard deviation is the width of your distribution. Right? If everyone got the same grade, the mean would be whatever the grade is, and the standard deviation is 0, right? Because everyone got the same result. Right? So standard deviation tells you how broad, how uncertain your measurement is. Right? If you're going to make an average, right? If you have in PChem lab, I ask you to make a measurement of this particle in a box. Tell me what the average position is. You're going to write L over 2. You're going to say, okay, the box is a meter, and I see it half a meter every time. That seems to be the average. And then I'm going to ask you for the error in your measurement. Right? What's the uncertainty? Well, that's this, right? The standard deviation. Right? And there's an inherent uncertainty to it. Right? I haven't said anything about experimental error here. Right? You could still have experimental error. You could still have random error. Right? You still have that. But even if you had a perfect instrument, right? Even if everything were perfect, and you have just the greatest box in the entire world, there's still an inherent uncertainty to the position of the electron, because again, the probability distribution is broad. It's not perfectly narrow, right? It's broad, so it has a deviation. It has an uncertainty to it. And this is that uncertainty. Right? So what you're going to find is that when you do this calculation, that the standard deviation increases as roughly n squared. Roughly as n squared. And so that's exactly what we saw as we went to n equals 1,000, right? The distribution got broader and broader and broader to the point where basically you had equal probability of seeing a particle anywhere. And I'll draw it again, just to remind you. All right, n equals 1, psi squared looks like this, right? And n equals 1,000. Right, so here's the mean. It's the average value, and the standard deviation is like something like this. Right, it's got some width. Right, and n equals 1,000. Basically, what the distribution looks like is something that looks like this. Something like that instead. Hopefully, everyone can see that. Right, and so again, the mean is still right in the middle of the box. But what's the standard deviation now? Well, the standard deviation is the entire damn box. Right? It spans the entire width of the box. It's flat. Right? So here, in this case, sigma x, the standard deviation of n equals 1, is probably less than L over 2. Right? Which means that, again, it seems like in general it kind of wants to be near the center, but not exactly, right? It wants to be kind of on the edges of the center, but it doesn't like to be at the edges of the box. But here it doesn't care, right? Here the sigma of x is probably close to L over 2, right? There's basically equal probability of being anywhere in the box. It still has an average, but there's equal probability of being anywhere. And so the standard deviation just gets large, and it's going to approach the size of the box, right? And that's what happens in classical particles, right? Classical particles, you have an ideal gas in this box. The standard deviation of your measurement of its position is the whole box, right? Because it fills the space equally, right? The density of your atoms is equal at every part of your box of gas, right? So that's what we should expect, and that's exactly what the particle in the box tells us, is that as the energy gets higher and higher and higher, n gets larger and larger and larger, the particle basically fills the entire box. And you have equal probability to find it anywhere, right? Just like we expect. All right, so sigma x, the standard deviation, or the variance, tells us a lot about our uncertainty. It is the inherent uncertainty that we have. And everything that we measure in quantum mechanics always has an uncertainty. There's no definite measurement in quantum mechanics. It's always an uncertainty. Sometimes we can do tricks to make that uncertainty really, really small, because it is, by all means, a very, very precise science. Right? There are things in quantum mechanics we can measure to 11 or 12 significant digits. You know, have a relative error of 10 to the minus 10, or really, really small errors. But that error is ultimately bounded by this. There's some intrinsic physical uncertainty to our measurement that we can't get rid of. And this is true everywhere. A really, really interesting experiment. Are we done in 5 minutes? Yes. Oh man, I've been talking a lot. Great. Okay, so that's fine. That's fine. There's a really, really interesting experiment you can do. People have built detectors where you detect a single photon, single light particle. Very, very hard to do. It's very easy to find a single electron, turns out. Very, very hard to detect a single photon. And people find, okay, imagine you just have one little light particle just transmitting, right? You would imagine it would be noiseless. Right? There would be no intrinsic noise to this single photon because there's nothing to give it noise. It doesn't have a temperature. There's no thermal energy to give it noise, no black body breaking, nothing crazy like that. There's no noise to it. There might be noise in your detector, but you can model that, right? So you subtract the noise out of your detector, and you detect maybe 1 photon or 2 photons or something like that, and you find your signal is very noisy. You get a wave. So at n equals 1, you get a wave maybe. This is when you detect 1 photon. So 1 photon measurement, not n equals 1 like the first excited state of the system. But you get a wave that's very noisy like this. When you detect 1 photon, and then when you detect, say, 10 photons, again, you've subtracted all the experimental noise out. You see the same thing, you see the same phase, but the noise has gone away. This noise right here, right, this is time versus energy, if you will, roughly. There's some uncertainty to this. So our measurement of energy of our photon actually fluctuates. So what this means is that the measurement of energy, again, the average energy that we measure at a given time is well defined because it's a sine wave of a single frequency. Right? So we have the same points in both measurements. So the average is still the same. The average is independent of photon number, because the average, again, is just the sine wave itself. But the uncertainty of the energy squared is dependent on photon number. So what's actually happening is that you get this intrinsic noise, not because you don't know the energy of the photon. You know that exactly. It's a sine wave. You can measure the frequency of it. Right? Remember, E equals hv. So the average energy is E equals h times the average frequency you measure. Well, I can fit a sine wave perfectly with this data. Right? I know the frequency very, very well, but I still have noise. So where's that noise come from? Well, the fact of the matter is there's some intrinsic uncertainty to our measurement in the noise and the energy. The amplitude of this wave is proportional to the energy. The amplitude squared is. But anyway, regardless, there's some uncertainty to our noise measurement for the same reason why there's some uncertainty for our position measurement in the particle in a box. This is called quantum shot noise. Again, this is a very, very off-topic thing, but I think it's really interesting, is that when you measure energy, right, this is the most fundamental unit of energy you can measure, one light particle. There's no way to make anything more fundamental than that. There's some uncertainty to your measurement because there's some intrinsic uncertainty to the wave function of this photon. Right? The wave function of the photon, the idea is that if you instead look at the psi squared for this photon as a function of energy instead of position, it's not a single line like this. It's not like that, right? That's what you would think here. Right? Every photon has the same energy. It has the same amplitude. You just get a nice sine wave. That's what would imply this spectrum. But instead, it has some width to it. Right? So the one photon, this is the psi squared when you use energy as your variable. And it has some uncertainty, right? And that uncertainty is this width. Right? So when the particle is oscillating, your measurement of its energy, its oscillation, has some uncertainty proportional to this width. And so you get this intrinsic noise that you can't get rid of. It's always there. And people have done very, very sensitive measurements. And what it turns out is actually the way that this noise disappears. So like as you add number of photons, how much smaller does the noise get? It scales differently than normal noise. So normal noise scales as 1 over the square root of n. Right? So to like in NMR, like when you take averages of a spectrum in spectroscopy, if you take 4 averages, your noise will be 2 times less than for one acquisition. It goes as 1 over the square root. But quantum shot noise goes as 1 over n. So the noise level of 10 photons is 1/10 of 1. And if it were normal noise, thermal noise, things that you would find in your detector, it would go as 1 over the square root of 10. Right? It decreases more slowly. So people can show that this goes linear. And so it's this intrinsic noise due to the fact that we have some uncertainty in our measurement of the energy. Right? You can't get rid of this. It's always there. And this has deep consequences, right? In chemistry and in physics and everything. Right? We'll explore that. But I think this is a nice time to think about it. Because now, with all of this, you have some tools to really start thinking about the homework. Okay? We've done everything you need. You know how to take averages. You know how to take standard deviations. You know what the wave functions are. You know what the energies are. It's all you need. You can start doing quantum mechanics with that. So we'll come back and we'll start talking again. We'll return to the particle in a box on Monday. Do some more tricks. Learn a couple more postulates. Learn a few more things. We haven't talked about momentum yet, so we're going to think about motion. All right, we'll do that on Monday. All right, you guys have a good one.
See you next week.
Yeah, take care.
Have a good one.
You too.
Have a good week.
You too. See you Friday.
Have a good weekend.